All right, I'm going to revisit looking at vectors, say, of this form. And we showed that this was a subspace, or things that look like this, right? This is a subspace of R3. So I showed you that we could factor the t out, right? And that gave us -1, 2, 0. And so if I identify this vector here as v sub 1, then the subspace H could be described as the span of v1. And let's think about it. If I have a span of a vector, does it satisfy the criteria for subspace? Yes, because there is a zero vector, right? I could let the t equal 0. It's closed under addition because that's what happens is I have linear combinations of that vector, so it's always going to stay in the span of that one vector. And it's closed under scalar multiplication because I'm allowed to let this constant in front be anything. So the span of a vector is a great way to say it's a subspace. This is going to be, we will find out, it's going to be the easiest way to describe a subspace. So if I have span of a set of vectors, it is a subspace. Span of a set of vectors is automatically a subspace, and you don't have to go through checking 1, 2, and 3. So good facts to know, subspaces of R2 would just be like the zero vector R2. Lines through the origin in all of R2. So all of R2 would be everything, right? A line through the origin, right? Something like that. And then just the zero vector, just like that. So subspaces of R3 would be the zero vector, right? A line through the origin. Let me just do it in a different color so you can see it. A line, whoops, line through the origin. A plane through the origin, right? A piece of paper flying through the origin has to go through the origin, right? Because I have to have the zero vector. Or all of R3, which would be everything, right? Okay, so those are just examples, just to compare and contrast the difference between R2 and R3. So this is the most common way of describing a subspace by saying it's the span of a set of vectors. All right, so is this set W? Can I write it as the span of a set of vectors? If I can, then I'm done. It's a subspace. So let's see if I can factor out an S and break it up and factor out a T, right? Make this my vector 1 and this my vector 2. And then if I can say that W is equal to the span of V1 and V2, I'm done. Because then I know it's a subspace. Right? That's my goal, is to be able to say, oh, I can rewrite W as a span of a set of vectors, so I know it's a subspace. So can this be done? I can pull out a 1, 1, 2, a 0, and the factors with T in it, -1, 2, 1, and 4. Yes. So this vector can be broken up into these two vectors. So I've got any linear combination of this and this gives me the span, and that gives me the subspace W. All right, let's look at these. All right, so I've got V1, V2, V3, and I'm looking to see if W, and I've got part A and part B here, sorry I didn't label them well, part A and part B. So part A is saying, is W in the span of these three vectors? So what this is asking is if can I take a C1 times V1 plus a C2 times V2 plus a C3 times V3 and get to my W? Well, that sounds like an augmented matrix to me. So let's do it. 1, 2, 4, 1, 0, 1, 2, 0, -1, 3, 6, -1. I put it into my calculator. 0, 1, 2, 0, 0, 0, 0, 0. Okay, so let's think about this. What I'm looking at is I see that I have a consistent system. It's not asking me what the solution is, not asking me that, but I see I have a consistent system. So yes, W is in the span of V1, V2, V3. All right, so is it true that Z is in the span? So again, we're just going to put together the augmented system here. 4, -1, 3, 6, 7. Put it in my calculator, and I get 0, 0, 0, 1. Okay, because I know I'm looking at an augmented matrix, right? This is an augmented matrix. This last row gives me the conclusion that, whoops, that it's inconsistent. Inconsistent. Because this last row says 0 equal 1. So no, Z is not in the span of these three vectors.